el honorable doctor Franklin García Fermín, ministro de Educación Superior, Ciencia y Tecnología de la República Dominicana. El doctor José Alejandro Aybar Martín, canciller de Unicaribe. El ingeniero David G. Arellano, director general para Latinoamérica de Keysight Technologies. Y es un privilegio contar con la presencia en nuestro país y de manera particular en este auditorio de nuestro invitado especial, el ingeniero Paul Hoffman, presidente de Sapient Focus. Bienvenido, señor Hoffman, a República Dominicana y a la Universidad del Caribe. Resaltamos la presencia del honorable ministro de la Juventud, el señor Félix García, también del viceministro de Zonas Francas y Regímenes Especiales del Ministerio de Industria, Comercio y MIPYMES, el señor Johannes Kellner, a la señora Marie Laire Aristi, viceministra de Políticas de Empleo del Ministerio de Trabajo, así como a los magníficos rectores que nos honran, nos privilegian en esta mañana con su presencia. En nombre del Ministerio de Industria, Comercio y MIPYMES, les doy a todos la más cálida bienvenida al programa de formación, introducción a los semiconductores, integración, empaque y ensamblaje. Un encuentro de capacitación que tiene como objetivo incentivar e impulsar la formación profesional, técnica y operativa relacionada a la industria de los semiconductores, respondiendo al decreto 324-24 que en junio de este año dictara el presidente Luis Abinader y que en su artículo número 324-24 reza así. El presente decreto tiene como objetivo declarar de alta prioridad nacional la promoción, la innovación y el desarrollo de la industria de los semiconductores en la República Dominicana, así como ordenar la formulación de las estrategias nacionales de fomento a la industria de semiconductores y sus planes de acción con la visión de apertura al mercado internacional, de atracción extranjera, de inversión extranjera y de posicionar al país como un destino estratégico, competitivo y confiable para esta industria. Así que estamos felices de contar con ustedes, estudiantes que comparten el entusiasmo por la tecnología en este curso de formación rápida que les introduce al mundo de los semiconductores, materiales fundamentales en la fabricación de los componentes electrónicos que son esenciales para el funcionamiento de dispositivos que usamos en el mundo moderno, que utilizamos día a día, como el caso de los celulares, de nuestras computadoras, los electrodomésticos, incluso los automóviles. Este programa de formación se desarrollará en este auditorio del Banco BDI de la Universidad del Caribe y por eso invitamos para las palabras de bienvenida a su canciller, el doctor José Alejandro Aybar.
Muy buenos días, ministro Ito Bisonó, ministro de Industria, Comercio y MIPYMES. Buenos días al doctor Franklin García Fermín, ministro del Ministerio de Educación Superior, Ciencia y Tecnología. A la doctora Marilaure Aristi, viceministra de Trabajo, quien representa al ministro Luis Miguel de Camps, ministro de Trabajo. A nuestro invitado, instructor del día de hoy, Paul Hoffman, presidente de Sapient Focus, al ingeniero David G. Arellano, director general para América Latina de Keysight Technologies, José Gior Ariza, a Johannes Kellner, viceministro de Industria, Comercio y MIPYME, a los estudiantes de todas las IES que nos acompañan hoy, un aplauso para ustedes por aceptar este llamado, a que se unan a este importante evento, que será un antes y un después en el inicio de la formación de los semiconductores en la República Dominicana. A los rectores, don Franklin Holguín H. de UNAPEC, José Ramón Holguín de ITSC, a Rafael Félix del ITLA, a Huáscar Fría de UTESA, a Radamés Silverio, vicerrector de la UAS, demás vicerrectores, a Ricardo Winter, rector de UPIT, a todos los viceministros que nos acompañan, a demás autoridades académicas, invitados especiales, buenos días a todos. En una visita al ministro Ito Bisonó para informarle sobre la apertura con doble titulación Unicaribe Tech de Monterrey de la maestría de inteligencia artificial, surgió el tema de los semiconductores y la gran oportunidad que representaba para el país y del interés del presidente Luis Abinader en encontrar nuevas alternativas para mejorar la economía de los dominicanos. Aprovechando la propuesta del nearshoring, entendimos la importancia que representa esto para la República Dominicana. El empeño de nuestro presidente Abinader y del ministro Bisonó ha sido fundamental en este proceso, culminando con el decreto del que hacía referencia Laura, el 324-24, que declara de alta prioridad nacional la promoción, innovación y desarrollo de la industria de semiconductores en nuestro país. Este decreto invita a todos los sectores, público, privado y académico, a unirse en un esfuerzo conjunto para posicionar la República Dominicana como un destino estratégico y competitivo en el mercado global de semiconductores. Conscientes de esta visión, nos llevó a presentar una propuesta al MESID de un técnico superior en tecnologías de semiconductores y convocar a varias universidades que también están haciendo un esfuerzo en el desarrollo del tema con la idea de crear un consorcio universitario en temas de semiconductores, ya que este esfuerzo unificado garantiza el éxito y asegura llegar al mayor número de estudiantes en el menor tiempo posible. Mientras avanzamos, nos informaron sobre una delegación dominicana que viajaría el pasado mes de julio a Semicon West 2024 en San Francisco, California, para explorar oportunidades con la industria de semiconductores. En nuestro caso particular, ya habíamos establecido contacto con la empresa Keysight y teníamos programada una firma de convenio, la cual programamos aprovechando la fecha de este encuentro. Al revisar el programa de Semicon West 2024, nos dimos cuenta de que el día antes de la convocatoria había 6 temas de formación relacionados con los semiconductores. Por ello, adelanté mi viaje y me registré en uno de ellos, que era Understanding the Business of Semiconductors, que se impartiría aquel lunes de 9 de la mañana a 5:30 p.m. Formación que ofreceremos próximamente en la República Dominicana luego de la autorización del señor ministro Ito Bisonó. Pero habían 2 temas que nos interesaban, el que tomé y otro sobre ensamblaje y empaque que se estaba llevando a cabo en un salón adyacente. Durante la hora del almuerzo crucé para asistir brevemente a esa sección donde tuve la oportunidad de conocer a Paul Hoffman. Le expliqué del interés de esta formación específica sobre integración, empaque y ensamblaje, vital para nuestra iniciativa y que sería útil realizar esta formación en la República Dominicana para que personas pudieran beneficiarse de estos conocimientos. Le pregunté a Paul si pudiera venir y hoy está aquí con nosotros, compartiendo su vasta experiencia con el tema de hoy. Gracias, thank you, Mr. Paul, y a su esposa por estar aquí con nosotros en la República Dominicana. Señoras y señores, estamos ante una oportunidad histórica donde las principales naciones del mundo están decidiendo dónde ubicarse para la producción o ensamblaje de semiconductores. Nuestro reto ahora es motivar a miles de dominicanos a enfocarse en esta industria, no con la tradicional idea de mano de obra barata, sino para atraer inversiones que ofrezcan salarios justos y competitivos, elevando así el nivel de vida de los dominicanos, tal como es la aspiración del señor presidente de la República, Luis Abinader. Agradecemos sinceramente la presencia de varios rectores, así como representantes de varias instituciones de educación superior aliadas al tema de los semiconductores y su compromiso con esta gran iniciativa. Nos referimos a UNAPEC, a UTESA, al ITLA, a la UAS, a UNADE, a OIM, al ITSC, a UPIT, a UNADE, a la UCE, a INTEC, a la Pucamaima y a Unicaribe, y otros que se integrarán en los próximos días. Así como nuestro agradecimiento a representantes del sector empresarial y de zonas francas de las diferentes localidades del país que nos acompañan hoy. Muchas gracias por estar aquí. Nuestras conversaciones con el sector de los semiconductores indican que debemos movernos con rapidez en la formación técnica, ya que se necesitan miles de técnicos capacitados en los temas que trataremos hoy, además de algunos ingenieros electrónicos. Estamos comprometidos con esta causa, trabajando junto a aliados como Keysight Technologies de California, como PC Precision Engineer de la Zona Franca de Santiago, para formar a nuestros ciudadanos y hacerlos competitivos tanto en el mercado nacional como internacional. Esperamos con ansia la visita de Satish Dhanasekaran, CEO de Keysight Technology, en la República Dominicana en el mes de octubre, lo que nos acerca a la posibilidad de establecer una presencia firme de una empresa líder en tecnología en nuestro país. Finalmente, quiero dirigirme a todos los estudiantes que hoy nos acompañan. Ustedes que representan el futuro del país y de esta iniciativa, tienen la oportunidad de apostar por el futuro de la República Dominicana. Un presidente y un ministro no pueden cambiar un país de manera aislada. Es con el apoyo de toda su gente, especialmente de los jóvenes, que es con que se puede lograr un verdadero cambio. Aprovechemos este momento histórico para la nación. Apoyemos firmemente esta iniciativa y aprendamos todo lo referente a este tema, una puerta a nuevos horizontes para la economía dominicana. Promuevan la formación de semiconductores en todos los niveles y junto a la academia hagamos posible que la República Dominicana en los próximos 2 años, con al menos 10.000 dominicanos capacitados, que puedan garantizar la confianza de las empresas del sector en invertir en nuestro país. Muchas gracias, ministro Bisonó. Muchas gracias, don Franklin García Fermín. Gracias, David G. Y sobre todo, muchas gracias, Paul Hoffman. Gracias por estar aquí y hacer de este día uno memorable para la República Dominicana. Muchas gracias a todos los presentes y que disfruten de esta jornada de formación con nuestro experto invitado, Paul Hoffman. Éxitos.
Entusiastas las palabras del canciller de la Universidad del Caribe, José Alejandro Aybar Martín. Y bueno, los semiconductores son la base de casi toda la tecnología moderna, desempeñando un papel crucial en todo lo que es la economía global. Pero ¿quién mejor para abundar sobre este tema que el ingeniero David G. Arellano, director general para Latinoamérica de Keysight Technologies, a quien le damos la bienvenida?
Buenos días a todos. Gracias, viceministro, ministro, canciller, por la invitación aquí. Buenos días a todos. En tecnología, el ecosistema se define como una unidad de diferentes entes independientes interconectables. Es una red en la cual trabajan de alguna manera en conjunto para un objetivo común, que es el desarrollo y crecimiento de un mercado o una industria. Existen muchos ecosistemas, está el de aeroespacio y defensa, está el de automotriz, energía, está el de quantum computing actualmente y está el de semiconductores, así como comunicaciones. Todos ellos de alguna manera tienen un factor común, que es lo que hace que sea exitoso o no en una región o en un país o en un área, y eso es la educación, ¿sí? Sin ellos, por más que exista la tecnología, existan todos los medios, si no existe una educación, un talento humano, no es posible, poder desarrollar eso. En Keysight lo entendemos como fabricantes de equipos de prueba y medición y también como fabricantes de semiconductores. Sabemos lo que es el reto que enfrentan las empresas, los países para desarrollar ese talento. Y es por eso que hace 1 mes y medio, cuando firmamos ese acuerdo de vinculación, nuestro objetivo es ayudar a la República Dominicana a través de las diferentes universidades en desarrollar ese talento que pueda de alguna forma ayudar a impulsar este proyecto, y va a ser un reto que todos vamos a tener que trabajar en conjunto. Es mi compromiso como empresa y esa es la razón por la cual estoy aquí, ¿sí? Para mostrar eso y entre todos trabajar en conjunto. Entonces, nuevamente les agradezco mucho su tiempo, ¿sí? Y espero que esta presentación sea exitosa para todos y tengan mi compromiso como empresa. Gracias.
Muchas gracias al ingeniero David G. Arellano. Y bueno, la creciente demanda de tecnología avanzada y la expansión en lo que es la digitalización han convertido a los semiconductores en un motor para lo que es la economía, clave también en lo que es el crecimiento económico y la competitividad global. Definitivamente, el desarrollo de la industria de los semiconductores en República Dominicana sería una gran oportunidad. Invito a este podium a quien lidera esta iniciativa, el licenciado Ito Bisonó, ministro de Industria, Comercio y MIPYMES.
Muy buenos días a mi amigo José Alejandro Aybar, canciller de Unicaribe. Quiero aprovechar para felicitarlo además por su iniciativa y todas sus energías que ha concentrado en este tema. Ministro Franklin García Fermín, señor Paul Hoffman, presidente de Sapien Focus, David, muchas gracias por el apoyo y espero que lo veamos pronto, nueva vez aquí, ¿verdad? En octubre, acompañando al CEO de la compañía. Y después en las instalaciones, que vengan aquí, viceministros, rectores, directores, estudiantes, amigos, amigas que nos acompañan el día de hoy. Es un honor y un privilegio como ministro de Industria, Comercio y MIPYME dirigirme a ustedes hoy en la inauguración de este trascendental programa de formación, el cual se titula Introducción a Semiconductores, Integración, Empaque y Ensamblaje. Considero este momento como un hito significativo en nuestra travesía hacia el desarrollo de la industria de semiconductores en la República Dominicana. Permítame comenzar contextualizando la importancia de este paso que estamos dando y que ya José Alejandro comentó un poco. Como ustedes bien saben, en un mundo que cada vez está más digitalizado, los semiconductores se han convertido en el corazón palpitante de la revolución tecnológica. Estos diminutos pero poderosos componentes son fundamentales para una amplia gama de dispositivos que van y forman parte de la vida cotidiana. Desde los teléfonos inteligentes que llevamos todos, ¿verdad?, día a día, hasta los sistemas más avanzados que impulsan cualquier tipo de empresa o tecnología. La semana pasada tuve el privilegio de participar en la conferencia del doctor Axel Zimmermann, un reconocido experto internacional en semiconductores, alemán, y que en el último mes nos acompañó para identificar el potencial de la República Dominicana en este sector y visitó empresas, instituciones académicas, entidades gubernamentales, las zonas francas. Bueno, le dio una vuelta al país. Y sus palabras no solo me llenaron de satisfacción y optimismo, sino que también validaron la dirección estratégica que hemos tomado como nación. El doctor Zimmermann declaró que la República Dominicana está preparada para adentrarse en mediano y largo plazo en el campo del ensamblaje, la prueba y el empaque, ATP, de los semiconductores. Por lo que estamos preparando para este gran desafío y oportunidad a nuestra estructura de capital humano, que serán muchos de ustedes. Esta evaluación positiva de nuestro potencial proviene de una autoridad de su calibre que refuerza nuestra convicción de que estamos dando los pasos necesarios y en el camino correcto. Así también lo señala un informe ICTIF del Departamento de Estado, que lo vamos a poner a su disposición y que es el primero que se presenta en toda América Latina. El programa que se inaugura hoy es una respuesta directa y contundente a esta oportunidad que se nos presenta. No es una coincidencia, es el resultado de una visión estratégica y de un compromiso inquebrantable con el futuro económico y tecnológico de nuestro país. El decreto número 324-24 que emitió el presidente de la República, Luis Abinader, declara de alta prioridad nacional el desarrollo de la industria de los semiconductores en el marco que guía nuestras acciones. Al capacitar a profesionales en las complejidades de la integración, empaque y ensamblaje de estos semiconductores, estamos sentando las bases para un futuro próspero en una industria de alta tecnología. Una industria que en República Dominicana ya ha dado muestra más que suficiente de que podemos dar un paso acelerado, y ahí están la producción de nuestra zona franca con medical device. Venimos de hace 50 años de un modelo que comenzó siendo textil y que ya está también en la más alta tecnología, y donde ya hay empresas en República Dominicana como Jabil y otras que están trabajando muy de cerca con los mismos procesos de semiconductores, o que desde aquí se ensamblan y se hacen equipos y maquinarias, como todo lo que tiene que ver con los cateterismos, que tienen que ver también con temas electrónicos y eléctricos muy sofisticados. Así que estoy seguro de que los participantes en este programa se convertirán en un pilar fundamental de nuestra estrategia nacional para desarrollar una industria de semiconductores robusta y competitiva a nivel mundial. Los invito a que aprovechen al máximo esta oportunidad de aprendizaje. Les deseo el mayor de los éxitos en este programa de formación y en los desafíos que nos esperan juntos en la industria de semiconductores. Y a los rectores de las universidades que nos acompañan, así como a los institutos y a los demás centros de formación de la República Dominicana, también los invito a poner atención, porque aquí hay un nicho muy interesante, muy grande, muy prometedor para nuestro país, de manera que estemos siempre a la vanguardia de los retos que nos depara el mundo. Muchas gracias. Buenos días.
Gracias a nuestro ministro de Industria, Comercio y MIPYMES por estas palabras. Y bueno, pues ha llegado la hora de pasar al plato principal de este día, y queremos informarles que la capacitación será dada en el idioma inglés. Así que para todos aquellos que así lo necesiten, tenemos unos radios de traducción que se encuentran en la mesa que está a su derecha, al extremo derecho. Pueden ir a tomarlos en este momento, pues ya estaremos entonces pasando a la parte principal. Agradecemos a todos nuestros invitados de honor, a aquellos que han formado parte de este escenario en el evento de inauguración de esta formación y capacitación, Introducción a Semiconductores, Integración, Empaque y Ensamblaje. Y al señor Hoffman que se nos quede aquí un momentito, porque en lo que bajan los señores, a quienes por supuesto si su agenda se lo permite, les invitamos a que permanezcan con nosotros, porque ha llegado el momento de embarcarnos en un viaje de aprendizaje que nos permitirá comprender mejor estas tecnologías y también descubrir de qué manera pueden ser aplicadas. Si así lo desean, las personas que se encuentran en el último bloque de asientos pueden sentarse de este lado, que hay muchos asientos disponibles, y de esta manera pueden estar mucho más cerca del instructor. Les invitamos a cambiar a esta columna de asientos. Mientras tanto, les cuento un poquito, permítanme hablarles acerca de nuestro experto internacional que definitivamente nos premia compartiendo su conocimiento en este día. Paul Hoffman es graduado de Ingeniería Mecánica en la Universidad de Stanford con un posgrado en Gestión de Ingeniería. Concluyó en el 2000 un programa ejecutivo de fusiones y adquisiciones en la Universidad Northwestern. En el 2025 completará una maestría en arquitectura en el Boston Architectural College. Desde el año 1982 ha ocupado las más altas posiciones en empresas dedicadas a secuenciación de ADN de próxima generación, enfriamiento de chips de circuitos integrados de alta potencia en servidores, equipos de telecomunicaciones y equipos militares, enfriamiento térmico para electrónica, ensamblaje y prueba de circuitos integrados, así como antenas internas. Desde el 2008 y hasta la actualidad es presidente de Sapient Focus, una empresa de San Diego, California, que proporciona servicios de propiedad intelectual y tecnología a diversos clientes, incluidos múltiples empresas de Fortune 200, compañías emergentes y también firmas digitales. Por 8 años se desempeñó como miembro del Consejo Asesor de la Escuela de Ingeniería de la Universidad Nacional de San Diego, California. Ha emitido 61 patentes estadounidenses en el área de electrónica, ensamblaje y sensores basados en grafeno para secuenciación de ADN, aplicaciones en proceso de identificación personal por aliento, una especie de huella digital, y otras intervenciones relacionadas con sensores para la salud móvil. Ha presentado 24 artículos en conferencias de electrónica y 7 artículos en revistas de la industria. Ha participado como presidente de sesión en múltiples conferencias. Y esto es un resumen ejecutivo de lo que es su biografía y su currículum. Con ustedes, Paul Hoffman. Disfrútenlo.
Gracias. So I'm very happy to be here. Thank you for inviting me, Jose. And for me, I usually give a technical presentation, which you will see is a technical presentation, but this seems to be so much more. And so I'm honored to be here and try and give you some idea of what packaging technology is like. I remember back to my days when I was at Stanford and interviewing companies and deciding what I wanted to do. And I had an interview with IBM, and they showed me a semiconductor chip, and they explained a little bit about it, and it just fascinated me. And so I hope that maybe something you'll find in my presentation today will be that kind of spark that fascinates you and makes you decide that, oh, this is something I want to find out more about and learn more about and maybe turn into a career. So again, thank you for inviting me. So it's, as I said, the course is quite technical. So I don't expect that you'll come away with, deep knowledge, but I hope that you get an appreciation for what packaging is, and as I go through and explain this. And the other thing you may get an appreciation for is, as many of the speakers said, semiconductor technology, and a part of that is the packaging of the semiconductors, is all around us, and it's pervasive. So it's in your laptops that are here, it's in your cell phones that you have, it's in everything. And so to understand more about how these devices work and how they're assembled, to me, is interesting. It's always interesting to understand how things work. So in terms of the course overview, there's kind of two main ways that I think of this and want to present this information. One is, how do you make it? And so we'll talk about that. We'll talk about the chip preparation and substrates and joining operations and encapsulation and many more details. And then there's also about how the device performs and where it might be used and what's important to various classes of devices and different applications. Let me skip. I think they gave a very nice overview of my background, so I appreciate that. But I'm showing here some pictures of some of the types of devices that I've worked on in my career. And so you're already starting to see and getting a flavor for what we mean by packaging, but I'll explain that more in a minute. This is not for you to absorb right now, obviously, but as with any industry, there's many abbreviations, so I wanted to put together a table that you could refer to later if you have some interest in this field. So basically, what is chip packaging? I would call it a house to protect the chip or components. And when I say chip, I mean a semiconductor chip. A semiconductor wafer that has been cut into pieces, and we call that a chip. Some people also call that a die. So there's those.
1 minute.
Yep.
So they can put the QR code so they can download.
Oh, of course. So to continue, some of the basic ingredients to make a packaged chip. You start with a chip or a component of some kind, but usually we have something called a substrate, and then a means to interconnect that substrate between the chip and that substrate. And then also some way to interconnect from what is now the package to what we call the next level of assembly, which is also often printed circuit board or PCB. And then also some way to encapsulate the chip and protect it. So these diagrams are very basic terminology, and I will explain as we go through, but there's various ways of interconnecting. Some shown here are wire bond interconnections from a chip to a package or to a substrate. Some are shown as flip chip bumps. There's encapsulation of different kinds shown here, such as a ceramic housing or a plastic mold compound, and other items that I'll describe. One of the main things that we talk about in packaging is whether the package has the chip facing up or the chip facing down. So it's pretty simple. You can see on the packages on the left, the chip is facing up, and on the right, it's facing down. And then we also talk about levels of packaging. So what we call the first level assembly is that assembly that encapsulates just the chip. And then that package, when it's assembled onto the next level of assembly, we call that second level assembly. So it was mentioned that J-Bill has a factory here. And what they do is what I would refer to as second level assembly. It's the assembly of components onto a PC board. And then there would be a third level assembly also at those PC boards going into a system. As I was describing, we all have electronics around us. So there's a picture there of an iPhone a couple generations ago. And what you're seeing there is, we call it the AP, but application processor, so kind of the brains of the phone. And you can see there, and maybe get an appreciation for how important that component is just by the size of it on the PC board that's in that phone. So the purpose of chip packaging, so it protects the chip from the environment, from humidity or corrosive gases, mechanical protection. So if you drop your phone, you don't want the semiconductor to stop working. It interconnects the chip to the second level package while meeting the performance requirements. It provides thermal pass because many chips operate at very high power, and give off a lot of heat that has to be extracted from the chip. And it must provide a reliable operation over the required product lifetime. And while it does all those things, it has to meet the physical requirements of the system as well as the cost requirements. So these are just some examples of, how a chip might be protected. So what you're seeing in this case is maybe the most minimal protection. It's something we call a wafer level package. So it's almost an extension of just the chip fabrication and wafer fabrication process itself. A few extra layers on the surface of the wafer are enough to package some components, especially for those that go into very thin applications. This describes some interconnects in a package. You can see here things like a lead frame and wire bonds on the left, and then flip chip bumps and bumps on the substrate on the right. In almost all cases, the package also is a space transformer. So you can see that at the chip level, the spacing of the pads, the bond pads that we connect to, are very tight. And then at the other end of the package, it starts to get wider. And this is very typical. So fabrication at the semiconductor level is at very, very small dimensions, and those have to be translated into wider dimensions so that the package can be assembled to a printed circuit board. And then there's many ways to provide thermal pass. As I said, not all chips, but many chips require some kind of thermal path to extricate the heat from the package. And so there's many different ways of doing that. We'll describe some later. And then, as I said, the package has to be reliable over its lifetime. And so I'm just showing here some of the kinds of ways things fail in a package. So you can just get an appreciation maybe. And so a lot of the time, if you're a packaging engineer and you're designing new packages, you spend a lot of time trying to ensure that these kinds of failure modes don't happen. And so it can be quite challenging, in fact. So wafer fabrication, if you're not familiar with the term, this is the process to create integrated circuits. And also the plants that make wafers are also called wafer fabs. And these are huge investments typically. Some of the latest factories are $30 billion US to make one wafer fab. So it's a highly sophisticated endeavor. There are many different kinds of fab processes depending on the device that is to be made, and that includes different semiconductor materials. Silicon is the most common, but there's many others like silicon germanium or gallium arsenide or others. There's also different types of transistors. So transistors are the kind of fundamental switches in the chip that form logic or other circuits. And we're probably most familiar with the term CMOS, but there's others shown here as well. And then also kind of the device type. So you may have a memory or logic or analog, and then specialized devices like image sensors or MEMS, micro electromechanical systems, power chips. And I'm just showing there some examples of what you would look like if you looked under an electron microscope at some of these devices, and they're all quite different. This is not really the part part of the talk in any level of detail, but just to give you some first appreciation maybe of what wafer fabrication is all about. It's really taken a semiconductor as a basis. So a semiconductor is typically grown as a large ingot and then diced into wafers, and the wafers are what the integrated circuits are formed on. And these wafers go through a number of processes like oxidation and doping and many repetitive steps of patterning, etching, and deposition to be able to create both the transistors and then the interconnects that are on top of the transistors. So this is what a wafer looks like. There, the picture on the bottom is the full wafer, and then a more close-up view of that wafer. And you can see a repeating pattern. So those repeating patterns are the chips that are on the wafer. And wafers are really the input to the packaging process. So what comes out of the fab goes into the packaging and assembly process. And critical for packaging in terms of the wafer are the interconnects on the wafer. So that's the metal layers that connect to the transistors in the lower levels of the wafer, and then come to the exterior part of the wafer so that we can connect to them at the package level. And so I'm showing here some images of what those interconnects look like for some different technologies. So the one on the left has copper interconnects. The one in the middle has aluminum interconnects and tungsten vias. And then the one on the right is kind of showing, again, similar to what I said about packaging. Even on the chip, there's kind of this space translation. So you can see at the very bottom, very, very tiny interconnects. And at the top, very large and widely spaced interconnects. So there's this progression even on the chip of going from something very small to something larger that can be dealt with. And at the package, that happens again. So these chips, again, as I said, the fabs are very expensive and the chips are very complex. So for, a processor chip that's state-of-the-art, it may have 15, 17, 20 layers of metal on it and 15 miles of interconnect on one chip, which is kind of astounding, really, to think about. So it's those interconnects that come to the surface in what we call bond pads. And bond pads for packaging people are the critical location for an interconnect. And so that's what we care about most on the chip. There's different ways to arrange those bond pads. There's typically a last layer of dielectric on a chip called a passivation layer. It's really a protective layer. And so that passivation layer can either be to the side of the bond pad or overlap the bond pad a little bit. There can be another final material that we call a stress buffer that might go over that passivation material. So that's what those diagrams are referring to. In terms of chip design, bond pads are typically in one of two fashions. Most often, the chips are designed with I/O cells. So these are specialized circuits that take the signals from the chip and send them out, or there can be receivers that receive from the outside and bring signals into the chip. And associated with those I/O cells are bond pads. And those are typically all arranged around the perimeter of the chip. But in some cases, especially for dynamic RAM memories, the orientation is down the center of the chip. And this has implications for packaging because we have limitations about how far we can reach a wire bond, for example. So I thought one way to organize this kind of material is talk about building blocks. So to me, a building block is kind of a fundamental process that we use to form packages. And if you work in the field, you start to learn about a number of different fundamental building blocks. And then in packaging, oftentimes we just kind of rearrange these building blocks to be able to create a different package. So the first building block I'll talk about is wafer thinning. So especially for portable applications, we want the overall package to be thin, which means that we also want the wafer to be thin or the chip to be thin. And so thinning has become quite a standard operation. You know, back when I started packaging, we never thinned chips. There was really no need. Everything was going into a computer that was large size, but now with cell phones especially, everything is thinned. So a 300 millimeter wafer, which is kind of the standard state-of-the-art wafer size, starts at 780 microns thick, but they are often thinned to 30 microns. So almost all the material is removed from the wafer before it goes in the package. And as a reference, copier paper is 100 microns thick. So it's very thin. And you can see there on the picture on the right, when you thin a wafer, even though it's a brittle material, it all of a sudden becomes flexible. And so this wafer thinning process is, I always think it's kind of funny because it seems kind of a very basic technology. You're essentially grinding it with grinding material. There's nothing very exotic about it other than you have to control it very well. Rough grinding and then a fine grinding and if need be some other processes to make sure there's no scratches on the back of the wafer. So the next building block is, we call it dicing. So that's the step that cuts the wafer into individual chips. So as I said, and then we showed in the picture before, a wafer has a number of chips stepped across it, repeating pattern, and we need to separate those so we can put those in the package. And typically, there's something the area that separates those chips on the wafer we call a street or a saw street. And ideally, you would like that saw street to be as narrow as possible because then you get higher utilization of the wafer. So that relates also to the dicing process. And there are a number of different ways to dice. The kind of traditional and has been used for a long time is a saw process. And that's literally a saw. It looks like a circular saw, specialized with abrasive material on it that cuts through the silicon or whatever the wafer material is. But there's other ways too. Sometimes lasers are used. There's something called stealth laser where the laser is focused on the interior of the crystal structure of the wafer and actually dislodges the crystal structure so that it can be easily broken and separated. And then there's plasma dicing. So if you're not familiar with plasma, it's a highly ionized gas. And it is good for etching. It's a typical etching process used in semiconductor fab, but we sometimes use it also in packaging and assembly, especially here in dicing operation. And then this is just some comparison between the different dicing processes. So blade dicing or saw dicing is the most common because it's the least expensive and easiest to implement. But it has some issues in that the sides of the chip sometimes are rough, and that can lead to problems of chipping and cracking. So laser ablation is another method, but leaves a lot of debris on the side of the chip. That can also be a problem. The stealth dicing is quite a nice process. The saw street is very narrow, and the edge quality is very high, but it's a little bit more expensive process. And then plasma dicing, likewise, small saw streets, very nice sides and edges of the wafer or chips when you're done, but the big problem there is you need a mask. If you didn't have a mask, you would etch everything on the wafer. So another key building block is a substrate, and I'm kind of broadening the terminology here to include lead frames, which I'll describe in a minute. But there's many different materials that can be used for substrates, ceramics. Laminate is quite common material. We call it laminate because many layers are laminated together. And it's essentially a PC board technology, but kind of shrunk down in terms of the spacing and line space and width. More recently, there have been silicon interposers being used. And so I'll describe that later, but maybe part of what you'll see through this talk is that there's kind of a blurring of the lines between what is traditionally semiconductor wafer fab technology and what is packaging technology. And so many of the things that an advanced packaging assembly factory does looks a lot like what might be done in a semiconductor fab. And then there's thin film and RDL. RDL stands for redistribution layer, and we'll probably hear me talk about that a number of times. I won't go through all this in detail, but let's say, there's many material properties that are important to the selection of the substrate. They have to do with thermal properties and expansion properties and electrical properties. So depending on what your application is and the type of chip that you want to package, there's a wide range of material that you might consider. So this is what a lead frame looks like. It's a metal piece that started as a solid metal piece that is etched or punched to create a pattern. So you can imagine that this is relatively limited in terms of what you can create because you're starting with full metal and then through a subtractive process, processing it. So you're limited on things like line and space, and it's also all on one layer, but it's also the lowest cost option. So of all the devices that are made today, the vast majority are still using lead frames. And then there's a special, so I mentioned that lead frames can be etched, and we have a process that we call half etching, followed by a full etching. And we can create lead frames with a cross section like on the lower left. And we call this QFN, or quad flat pack, no leads, but essentially there's no leads coming out of the package like a kind of an older lead frame package would have. And so the package is quite smaller, it's thinner when it's mounted on a board, and it's quite good. And this particular package has really taken over in the last 10 or 15 years in terms of lead frame packages, and its use has grown quite a lot. You can, if you're very creative, etch lead frames so that they have arrays of pads on them for wire bonding and for connection to the board. So again, a picture here showing that kind of more complex lead frame. Not very much used because it is a little difficult to use. This same kind of thing. This one is a particular one where they pre-mold with what we call a mold compound and epoxy material before etching part of the lead frame and then etching the last part of the lead frame. And in that way you can kind of get routing structures that look more like a printed circuit board than a lead frame. Ceramic is a material that is still used today, although not nearly as much as before. So for a long time, Intel would package your microprocessors on ceramic substrates. When I was at IBM, that's all we used was ceramic substrates for the most part. But the industry transitioned, so Intel at some point realized that ceramic was not going to support the type of electrical performance that their microprocessors needed. So they essentially drove the whole industry to bring up laminate substrate capability. And so the world of high-performance packaging now is pretty much uses laminate substrates. But you can still find ceramic substrate packages in some areas. I'm going to skip that one. As I mentioned, IBM, when I was there, used ceramics, and they actually used them up. They were probably the last major company that I know of that transitioned away from ceramics. So even up to 2015, they were still using ceramic substrates for their high-performance processors. In some ways, ceramic is a laminate kind of substrate too, in that it's built up with many layers. So you can see the one on the right there was built up with 103 layers of glass ceramic. So if you're familiar at all with printed circuit board technology, that image on the top looks like a printed circuit board because essentially, as I was saying, it's the same technology as in printed circuit boards. So this is what I would call kind of a standard laminate material. There's nothing very special going on here. You have vias that go through the substrate, and those vias are plated up. Those holes that go through are typically drilled, so mechanically drilled. So they have a certain size limitation. And those layers of dielectric and copper are pressed together and glued together, and that's why we call it a laminate. So this is very common and very close to a printed circuit board. But when the industry just understood that they needed, more routing capability and higher density on the substrate, there was a realization that line space had to decrease, and so the way that was found to do that was to create small vias with lasers. So these laser vias are called micro vias. They're significantly smaller than what you can achieve with a mechanical drill, and so these layers on the outside are additive, what we call additive layers. So it's not a lamination anymore in the sense that there's no foils, copper foil layers being laminated, but there are dielectric layers and then built up conductive layers and vias. And I should mention HDI, that's on the title there, that stands for high density interconnect. So it's how we describe these kinds of substrate materials. So these are just showing some pictures of HDI laminate materials. So the micro via process is quite flexible. You can stack the vias on top of each other, or you can offset them in what we call staggered vias. You can bury them inside the layers of the substrate. So it's quite a nice technology, and especially for packaging, it's essential for some of the high performance parts. It's a little difficult maybe to see these diagrams, but there are two processes shown here. One is called a semi-additive process, and then the other one's called a modified semi-additive process. But essentially what's going on is you create a via with a laser, and then you condition that via, and then you put a very thin layer of conductive material that can be used as a plating bus, and then you electroplate copper into the via and above the via, and that forms both the via and the interconnect trace at the same time. And we'll see this similar kind of process come up later, but this kind of what we refer to as a build-up process is a really essential building block that's used, well, it's used in wafer fab, but it's also used in substrates and packaging interconnect technology. More detail here on these processes. So the substrate, especially for a high performance, highly advanced package, makes up about 50 or 60% of the cost of the package. So it's kind of a critical piece of technology, but also critical to find the right suppliers that can give you the substrate that you want. And there's not a whole lot of substrate suppliers in the world. But you can see also in the images on the right, the kind of greenish layers, those are individual slices of a substrate. So these layers are very complex. They can have large numbers of vias in them, and I'm talking like thousands of vias. And yeah, for complex and advanced packaging, you know, we'll sometimes have substrates that have 15 or 20 layers in them. So this is just images of a typical kind of substrate. This one's for a microprocessor. One thing I should point out is that in the HDI, that interior part that's formed with kind of standard PCB technology is called the core, and then the build-up layers are on the outside. And so you can kind of see there that size difference between the vias of that via in the core versus the micro vias on the top there. So when the drive came for portable devices, and in particularly cell phones, there was a push to kind of shrink the vertical dimension of everything because people didn't want to carry around thick phones. And so essentially everything in the system had to shrink vertically, including the substrate materials. And so one of the reactions to that was to develop what we call a coreless laminate. So there is no core material now. So the picture on the left has a core, and the picture next to it is coreless. And so we're just using the build-up process by itself to build the substrate. And it has the advantage that it's much denser, much thinner, but it's also more flexible, and it becomes more difficult in the packaging and assembly operations. So critical and similar to the chip, where we had bond pads on the chip, we have pads on the substrate too, where the chip is going to connect, or its interconnect is going to connect to. And those bond pads have to have a finish on them. We call it a surface finish that is the right kind of material that we can bond to and bond to reliably. And so I'm listing there a lot of different surface finishes. But suffice it to say that it's a critical part of the interconnect. And then more recently, for very highly advanced processors, and I'm talking about like the most advanced GPUs and CPUs and things that might go into artificial intelligence systems or high-performance data centers, people are turning to silicon interposers. And the primary advantage of a silicon interposer is density, right? Because you're building this in a wafer fab process, typically at an older fab node like 65 nanometers, but something much more dense and fine that you could do in a laminate technology. So this comes in different flavors, but the one that's most in use today is what we call an interposer. So the chips are mounted to this interposer, and then the interposer is mounted to a package substrate. And we would call that whole thing the package. You know, what's the motivation for using an interposer in the first place? And I'll talk about this a little bit more later too, but essentially it's this idea of how closely can you pack the components and devices that need to communicate with each other. And so the closer you can get them together, the faster speed that you have of communication, the overall higher performance of the overall device will be. The big downside to, well, there's two big downsides to silicon interposers. One is that they're very expensive, and the other is that there's not a whole lot of suppliers. So essentially you're limited to going to the fabs for these, and the fabs don't generally want to make these because they can make more money on an integrated circuit wafer than making an interposer. So silicon is the material of choice for interposers. The interconnect is a damascene copper. So it's a copper that's inlaid into etched trenches in the dielectric layer. And the other significant feature is that it has what we call a through silicon via, or a 2ESV. So this is a specialized kind of, we call it deep reactive ion etching, or dry process, sometimes called the Bosch process because it was developed by a company named Bosch, that cuts all the way through the silicon wafer from the front side to the back side. So this was the maybe one of the first commercial products that came out. I think this came out in about 2010, 2011, I guess it's listed there. And it kind of shows you this concept where the chip is sitting on this interposer, and the interposer is sitting on the substrate. And again, it's this kind of what I described before, this requirement to go from very fine pitch to wider and wider pitch, and we're doing it twice in the package here. So you're starting with micro bumps on the chip that are at 45 micron pitch, and then on the bottom side of the interposer we're at 210 micron pitch, and then at the bottom side of the package substrate we're at 1,000 micron pitch. So at the same time that the pitch is changing, typically the numbers of interconnects are changing. So you can see on the chip there's 200,000 microbumps. On the interposer there's 20,000 microbumps, and then on the package there's 2,000, we call it BGA or ball grid array balls. So I guess over my career it's been pretty astounding to me to see the numbers and the density increase in interconnects at the packaging level. So when I started out, if we had a chip that had 1,000 interconnects on it, that was pretty dense. And now we're looking at chips that easily have, in this case, 200,000, sometimes 400,000, 500,000 interconnects on them. It's pretty astounding. I'm not sure that you may have ever heard of something called the memory wall, but if you look at that graph, this is kind of talking about the performance increases in processor speed over time versus the performance increases in memory over time. And there's this big gap. The performance of microprocessors has increased substantially at a faster rate than the performance of memory. And so we call this the memory wall, because a processor normally has to reach out to memory for instructions and for data to be able to operate. And so this ultimately also ends up being a packaging problem. How can we try and get the performance of the memory and the communication between the processor and the memory to perform as best as possible? So one way to do that is to take the memory off the printed circuit board and put it on the package itself. And I'm showing there one package that we did, and this is going back 20 years when I was at Amcor and we were working with Cisco, and they were trying to address this problem. And so what we did is we brought the memory onto the package substrate itself as a way to address this problem. And it's the same thing that's being done today. But in this case, in the lower right, that's a GPU processor with the memory brought right onto, in this case, a silicon interposer, so that it's as close as possible. And those connection lines are as short as possible from the memory to the processor. The materials, and I guess for the students out there, if you're interested in, what makes up packaging and where can you find a way into packaging, there's lots of different paths. You don't have to be an electrical engineer. You could be interested in material science. You could be interested in chemistry. You could be interested in digital design and CAD systems. Personally, I'm a mechanical engineer, which seems kind of odd, but that's how I got in. Anyways. So we talked a little bit about the silicon interposers, but the laminate substrates, we also call them organic, and they can be used as interposers too. So you see the picture there with kind of the red metal lid on it. So we have an organic or a laminate interposer on top of another laminate substrate. So again, it's all about kind of that challenge of going from the very tight pitch on the chip to a less tight pitch at the board. So I mentioned before RDL, or redistribution layer. So a redistribution layer is kind of built in a fab kind of technology. It's a material that's applied, dielectric material applied at the wafer level, and interconnects that are applied at the wafer level, but at sizes and pitches that are not nearly as tight as a typical wafer interconnect. And so we kind of use this also as a way to translate from the chip scale to the package scale. The nice thing about it is it's very flexible, and also it can be done at the wafer level. It means that it can be done all at once on many different chips. In addition to interposers, there's something that we call bridges. So within a laminate substrate, we might put a little piece typically of silicon, and you can think of it as a little silicon interposer, but we call it a bridge because it doesn't extend all the way across the substrate. And it essentially forms a bridge between two chips that are packaged above. So in the sorry. You can see here, this is a normal route in a package substrate, and then the red is showing, the communication between chips and an interposer. But a bridge has highly dense interconnect, but just very locally. And so the chips would be designed to have interfaces there, communication interfaces that are very dense just on those edges of the chip that connect to the bridge. Oops. That's not it. Maybe the tech guys can help me with this. Okay. Nope. I apologize for not knowing how to run this. There we go. So this is an example. This is an Intel part, FPGA, field programmable gate array, where they're using bridge chips. You can see there between the FPGA itself and then some transceivers that are on the package substrate, and embedded in the substrate is the bridge chip. And this is the same part. This is the same part, and you're looking at kind of in that left middle picture. You're looking at the density difference between the micro bumps that attach to the silicon bridge versus the bumps that attach to the substrate. So you can see the density and pitch difference there. The bridges or interposers can be active or passive, and by that I mean that what we've looked at so far are called passive. They're just interconnect. They have no functionality otherwise, but they could be another chip. And so it hasn't happened yet, but very soon, maybe in another year or two, we should start to see products coming out where that bottom chip or bottom interposer is not just an interposer, it's also a functional chip. And so it's going to be a part of the overall function of the package and device. So when I talk about RDL, I'm talking about a kind of technology we call thin film technology. And thin film is just generally some kind of film that's less than 25 microns thick. And typically these are deposited films in this kind of build-up process that I described before. And so I'll talk a little bit more in a second here about the different types of thin film, RDL, redistribution layer. But again, this is a fundamental process, so I'm showing it again here on the bottom just so you get an idea. In this case, we're building these films on the wafer. So we're starting with a wafer. We're going to coat some kind of photo-imageable dielectric. We're going to image that with a mask to create a pattern, develop it to create that open via. Then we sputter a metal seed layer, very, very thin layer, and then use a photoresist and pattern it to make a pattern in that mask of where we want the interconnects to be, and then we use that very thin seed layer as part of a plating bus to electroplate the copper up into that pattern. And then we remove the photoresist and we etch the part of the seed layer that was exposed and not under the interconnect, and we end up with this built-up interconnect layer. And if we do that, we can do that at the wafer level, or we can do that over a mold compound or epoxy mold compound. You'll see I put EMC sometimes here for epoxy mold compound. So in some cases, we dice the wafer into chips, but then we kind of make a new wafer using mold compound, but the chips are separated in case we need more room for I/O, and then we can build this thin film RDL layer, not only over the chip, but over the mold compound also. And when we do that, we call it a fan-out chip because we're fanning the interconnect outside the edges of the chip. And these can be built up in multiple layers. You can kind of continue this process essentially as many times as you want. So I mentioned before that the silicon interposer, one of the downsides is that it's very expensive and there's a limited number of suppliers. So in the industry currently for high performance packaging, many people are looking at using RDL interposers or fan-out interposers as a substitute for the silicon interposers. So again, just to summarize and again think about some of the key concepts here. So the purpose for an interposer or bridge to begin with is to be able to get very short communication between devices. Sometimes that's to address the memory wall. Sometimes it's just for logic chip to logic chip communication. And we can do that in a number of ways through a silicon interposer, through a bridge, or through an RDL interposer, etc. You're seeing here kind of the scaling of the routing density, essentially. And so you can see here the substrate, normal laminate substrate or HDI substrate is kind of limited. The fan-out is an RDL thin film type of technology, and then the silicon interposer or bridge. So again, the silicon is the best, but also the most expensive. I guess I'm in the first sentence there. I'm talking about something I haven't introduced yet, but something we call SIP, which you may not have heard of. You may have heard of SOC. So SOC means system on chip. So for a long time, the concept was everything in a system, we would try and shrink that down and bring it onto the semiconductor chip itself. And so chip sizes became bigger and bigger, 25 millimeters per side, very large, very complex, very expensive. And in contrast to that, there's something we call system in package. And that's the concept that you don't have to do all the integration at the chip level. Sometimes you can do that within the package itself. And that may be a better way to go. And for me, it's in your career when you look back, because I guess I'm kind of at the end of my career, I look back at things I'm proud of. One of the things I'm proud of is I came up with this terminology, system in package, and it was pretty widely adopted in the industry, so it's made me happy. But down below you can see kind of this contrast in picture form. So again, system on chip, trying to integrate everything onto the chip, and system in package, putting different kinds of chips in a package and use that as the basis for the integration. I'm sorry, this chart's probably a little hard for you to read, but essentially what this is saying is that for data centers, which are highly performance-driven applications for packaging, that there's going to be widespread adoption of what we call the 2.5D, so the interposer or 2.5D bridge over time, and then later to 3D, which we haven't talked about yet, but I'll touch on later. So again, for the data center, for performance, that's really what we've been talking about in terms of interposers and bridges. It's a performance-driven application. So this is just, and throughout here, I'll try and put in some examples of different types of devices so you can kind of get a feel for what these things look like in real life. And this is one of those. This is the Apple M1 Ultra. Probably came out 3 years ago, 2-3 years ago. So it's a very high performance engine for personal computers, but actually has very sophisticated packaging in it. So you can see in the upper right that's the whole package. That's the package substrate, and you can see multiple chips there, memory chips, the processor. There's actually 2 processor chips side by side. And then in the cross section down below, you can see that there's a silicon bridge there that is used to interconnect those 2 processors so that they could talk to each other at very high speeds. The other thing that you can see in this picture is there's something called a heat spreader. So that thick copper lid that's on the package is there to help get the heat out from these chips when they're performing. And kind of just more pictures of the same part. This is still the M1 Ultra. I guess in the lower right, you can kind of see that the silicon bridge below, those little lines on it are interconnects. And then above it is the actual integrated circuit chip. And you can see the scale of the interconnects on the silicon bridge are approaching the scale on the integrated circuit. So that's why the bridges are so valuable. Just to give you a sense of how these things are actually assembled, I'll go through the flow here. So oftentimes we use something called a carrier. A carrier is just a temporary device to hold the chips while we're processing them, but it doesn't end up typically being in the final package. So in step number 1 there, we're placing the chips on a carrier. And then step number 2, we're molding over the chips with this mold compound I mentioned, which ends up curing and being very hard. And then we actually grind that back to expose the bond pads. And then we're using the thin film RDL process I described to build up the interconnect layers. And we use that also to build up, plate up these tall copper posts. We call those TMVs or through mold vias because they're going to eventually go through another molding layer. And then that bridge chip is mounted on or interconnected to that kind of lower substrate we fabricated. The whole thing is molded again and ground again. And then more RDL is built up and connected over the top of it. And then finally we put some solder bumps on it and we flip that over and we solder that little part of the component to the larger package substrate and mount the memory on it. And then we add, we call it a stiffener on the outside to help keep everything planar, and a heat spreader, and put package bumps on, so larger size solder balls, and then that finally would be attached to the system board. So there's these kind of many process steps sometimes to make these complex parts. It gets to be, quite exacting how you do these processes. A lot of process control. To give you an idea, like in packaging factories where I worked, if you weren't hitting 99.9% yield on your product, so yield meaning, how many good parts, you put in 100 good parts, how many 100 starting parts, how many good parts come out. If you weren't at 99.9%, your process was out of control. So very, very high expectations and very lot of effort to make sure that everything is done right at every step. So I'll talk about now die attach material. So as I said, I use the term chip. Some people use the term die. It's the same terminology. It's that part that we diced from the wafer. And a die attach material is a material that can be used to attach that chip to the substrate. And so we can use something called die attach paste. So it's kind of this adhesive in a paste form, or a die attach film, same thing. Sometimes the die attach film is applied before the wafer is diced, in which case we call it a dicing die attach film. Over time, people in packaging have tried to, densify the packages and the chips in the packages. So one of the ways to do that is to stack chips. And die attach films are very important when it comes to stacking chips. If you have kind of a stair-step arrangement like this, it's pretty simple. You just stack them up using kind of your normal die attach film. And this is just an example, again, kind of a modern day example of what some of these things look like. So you've got a number of chips stacked here. This is actually an accelerometer and gyroscope. So this would be found in a cell phone. So, when you tilt your phone and your phone reacts, this is what's the sensor that's being able to understand that motion and allow the system to react to it. And so in here, you see a number of chips stacked using different die attach materials. And then these kind of loops that you see are wire bonds. So they're actually wires that are bonded from a bond pad on the chip to a part on the substrate. But as we try to densify more and more, especially in memory devices and especially in NAND memory device, so it's a type of flash semiconductor that's used for storage. So when you store a picture on your phone, for example, it's being stored in a NAND memory device. And as you know, all the phones and all our other devices, the need for memory is kind of unstoppable. And what that translates to in the packaging world is that we try and put more and more chips in a package. So you can see on some of these examples, it becomes literally crazy how many chips you're trying to stack together. So this also goes back to what I was saying before, that we need to grind the wafers very thin so that we can package them. And this is the reason why when you have a stack like this of 20 or maybe even 30 chips, you want them to be as thin as possible. And the die attach material in this case had to be developed to accommodate this because you have some chips that are the same size being stacked on top of each other. So the material has been designed so that when you do the die attach, it actually flows over the wire bond without harming the wire bond or disturbing it. Okay. So there's a number of different kinds of chip interconnection methods. I think if you would talk to most people in my industry and you said, what's a chip interconnect method? They would say it's wire bond, or it's something we call tab bond, or it's flip chip. But I like to expand the definition because when you actually look at how we make packages, we use more than those three types. So sometimes we use the printed wiring board microvia. Sometimes we use the thin film and build up RDL. We use through silicon vias, and we use something relatively newer called hybrid bonding that I'll explain more. So wire bonding is old. I think it first started in the 1950s, and so it is one of the original ways to interconnect chips. And it's literally stringing a very small diameter wire and bonding it to a bond pad on the chip and at the other end to mostly a substrate, sometimes to another chip, but it's done with what we call a wire bonder, which is a piece of equipment that is programmable. And if you go in a packaging factory, I have a picture of one there, you'll see, just huge rooms filled with these wire bonders, one after the other. So there's different types of wire bonding, ultrasonic wedge bonding or thermosonic ball bonding. They have different purposes and are tuned to different materials. So wedge bonding is typically used with aluminum wire, and thermosonic started out being gold wire, but as gold became too expensive, the industry has pretty much transitioned to copper wire now. You can see there in the picture on the right kind of what some of these processes look like. This is the thermosonic process. So the tip of the wire is actually melted to form this ball, because you'll hear this referred to as ball bonding sometimes. And that is thermo and ultrasonic energy bonded to the bond pad, and then the machine is programmed to translate that wire to the second bond pad, and then the bond is made there. So again, different types of materials are used for different applications, but copper has now become the most prevalent because of cost, versus gold used to be used most widely. And then, as I said, wedge bonding is mainly for aluminum and mainly for high power applications. So wire for wedge bonding tends to be much thicker in diameter. We call it heavy wire or heavy wire bonding. And you can see maybe the difference here on some of these. And in fact, for high power devices that have to carry a lot of current, sometimes, even the wire, aluminum wire, isn't enough. So it's developed into ribbons. So kind of flat rectangular pieces, and then even wider rectangular pieces, and then more recently putting in the package something we call clips that aren't wire bonded per se, they're solder connections, but they're able to carry a lot of current. This is just another example of clips being used here. So these are ball bonding examples. Again, this is back to the thermosonic process that would be used with copper or gold wire typically. And you can imagine there's a certain limitation on the pitch if you look at that picture on the left, because the ball has to be formed first, and that takes up more room than the wire. That limits how closely together you can put these. So, practical limit is maybe 50 microns, but real high volume limit is probably more than that. So it's definitely not as tight pitch as what we saw before for some of the micro bumps. We're at 25, 35 micron pitch. When we talk about stacking chips and the desire to keep the overall stack very thin, that becomes a problem with wire bonding, because the wire bonding typically the loop comes up before it goes down. So what has been developed is something we call a reverse stitch bond. But essentially you put down the ball part of the bond on a bond pad first, and then instead of bonding from the bond pad to the substrate, we reverse it. We bond from the substrate to the chip bond pad, but on top of that ball that has been previously placed. So that's what you see in the lower image on the right, where it's labeled reverse standoff stitch bond. But that bond started at the substrate and then was ended on the chip, which is not normal. But what that allows is a lower overall height of the wire. And so that's critical for thin packages, so that's quite often used in thin packages. And then oftentimes in memory, especially in NAND, as I was saying, you also have chip-to-chip bonds. So you can see there in some of these images that we're not only bonding from the chip to the substrate, but from chip to chip. Yeah, I think I won't. It's what I said before. So the pitch is limited, all right? It's limited by the ball size. It's limited by the bond pad opening. But, you know, in labs, maybe you can do 30 micron pitch, but in production, you're probably at 50 micron pitch and above. I thought this part was interesting because it's demonstrating both types of wire bonds in one package. So this is a power device with a controller in the same package. So the controller has higher I/O and less current. So we use thermosonic bonding here, and then the power has the aluminum heavy wire bonds. I think I'll skip this. This would be maybe for more advanced discussion, but it's kind of, when I look at this, I can see maybe a whole lot of things that are wrong with this assembly. And probably like anything, you know, over a long period of time working in a profession, you become very attuned to all the intricacies. I'm not going to spend a lot of time on tab. You will hear people refer to it as one of the interconnects in packaging, and it is true. It was actually also one of the original interconnects that was developed, but it has not really, you know, back in the 90s, I would say, people thought it might take over as a major interconnect scheme, but it never did. It's still in use today in some limited applications. So if you have a HP printer, I'm sure you have tab in it. So it's used to connect in essentially what's almost like a flex circuit film, or what we call a tab tape, to the inkjet head in that case. But also the other application that's widely used in is for drivers for displays. So flip chip, we call this flip chip because unlike more traditional and older packages where the chips are assembled with their face or bond pads up, in this case it's flipped over, so the face of the chip or the bond pads are facing down. So there's typically what's shown here and some of the terminology I'll describe. There's typically a bump on the chip that's going to connect to the substrate. There's often what we call an underfill material, and that material actually was one of the things that allowed flip chips to become into widespread use. So prior to the use of underfill, if the chips got too large, if the chip was on a laminate substrate, there's a differential expansion when temperature changes between the chip and the substrate would put a lot of stress on the bumps and cause bump failures. They would crack. And somebody tried and found out that underfill would reduce this cracking significantly. And so that allowed kind of the widespread use of flip chip. I guess on the right side, going from the chip downwards, you know, we have a bond pad, typically passivation layer, maybe a stress buffer layer. And then we have something we call UBM, or under bump metallurgy. So it's something like a pad finish that I talked about before that might be on a substrate, but this is on the chip level. And then there's a bump of some kind, typically a solder joint. And then on the substrate side, a pad finish and a pad and the substrate dielectric. So these can come in different flavors. Different companies, have developed their own style of doing this in terms of the details of the bond pads and the bump configuration. So you're seeing a couple different ones here. The Samsung one on the left, just the passivation opening and the bump formed in that opening. And then the one on the right has the stress buffer layer included. In general, a stress buffer layer helps to alleviate the stress that might be on the bump, again, from these kinds of package interactions such as differential expansion. So it turns out the UBM is quite important, and it kind of it has a lot of different requirements on it. That UBM has to adhere well. It has to provide a barrier. You don't want certain metals to diffuse into the silicon device. For plated up bunts, it provides a plating bus. Has to obviously have good electrical connection. So there's many different flavors of this that people have tried over time, but pretty much in the industry now, at least for copper bumps, it's resolved into a pretty simple structure of a titanium layer and a copper layer. Just in terms of scale, these UBM is very, very thin in comparison to the scale of the bump. So that's what this illustration is trying to show. In fact, sometimes that UBM is so thin that we can't really see it with a typical scanning electron microscope. We have to go to a transmission electron microscope even to be able to see it. So above the UBM is the bump, and different materials have been used for that over time. Solder has been for a long time one of the common bumping materials. Originally, we used to use something called eutectic solder that melted at 183, but because of the desire to get lead out of electronics, the industry has gone to something called SAC, or tin, silver, copper solder, which has impacted us in the packaging world because the melting temperature is quite a bit higher. It's 220 C, so we had to adjust all our assembly processes when that change took place. Let me skip that one. I'll skip that one. So solder is essentially used quite widely in packaging. It's used for wafer level packages. It's used for flip chip. It's used for something we call CSP, or chip scale packages. It's used for BGA or ball grid arrays. So this is just showing that solder bumps are all over the packaging world, but at different pitches depending on their package application. So this goes way back. This is a little bit of the history of how C4, the industry sometimes call these C4 bumps, and that stands for controlled collapse chip connection, was an IBM terminology. But this was back in the mid-60s, and they actually started out with copper balls that were coated with solder, but then transitioned to all solder balls. And you can see at the lower right there is a package of that era, and rather than packaging a semiconductor device, it's packaging one transistor. So today we have literally 50 billion transistors in some of the advanced processors, and this is just one transistor in that kind of huge package for it. So I'll throw this in there because it's kind of it's humorous to me. So I started at IBM. I started my career at IBM, and this was a report I wrote in 1984. And if you look at the two packages there, they're almost the same. And not much change from 1964 to what we were doing in 1984. And if you can believe it, we were still packaging memory chips with flip chip on a ceramic substrate at that time. It just, I don't know. I threw this in here too. This is just maybe indicative of how far the industry has come, and also relates to the factory that I worked in IBM. So on the left, you see what was 1 bit of memory that went into that system there, the SSEC system. So 1950-ish. And that went from electromechanical kind of, circuit to what we called core memory, so magnetic-based memory, but literally with a ferromagnetic core. And then to, well, what's shown on the right there was the industry's first million-bit DRAM chip. But if you can imagine trying to make a modern computer today with that old technology, you would have huge, huge rooms full of those kind of old wire relays. So in terms of, again, a little of the history, so both IBM and Delco were early proponents of flip chip technology, both working with solder bumps. IBM evaporated their bumps, literally heated up the solder enough that it would turn to a vapor and then condense on the wafer. And Delco stencil printed a solder paste to form the bump. But what's done today is more along these lines. And again, this is kind of the same kind of build-up process, so I won't go through it in detail, but it's the same kind of thought process as I showed before for RDL, where you're creating a seed layer, and then you're patterning it. You use the seed layer to plate up the bump through a photoresist mask. You remove that mask, etch off the seed layer, and you're left with what either a trace or, in this case, a bump. So this is showing on the top what the photoresist looks like when it's been imaged and patterned, and then on the bottom what the resulting bump would look like that would come from that photoresist mask. And on the right, on the top, you're seeing the bump as it's plated, so it's typically got some kind of a solder or tin alloy at the top. And it can be quite rough, but we don't really care because we're going to reflow it and then it becomes smooth. So again, just an example of where a flip chip might be used. This one happens to be in we call it a flip chip CSP or flip chip scale package. So in this package, on the right, you're looking at the chip with the bumps on its surface has been taken out of the package, and that would just mount to a substrate, a small substrate. And this is a cross-section of the same part. So that chip is flip chip mounted to the substrate, and then it's molded around it to protect the chip. And if you see in the top right picture, there's a lot of spheres in that mold compound. And that mold compound is highly filled, typically with silica or silicon dioxide fillers, so maybe 75% to 85% by volume of fillers, and that's to control the mechanical properties of that material. There's other kinds of bumps, depending on the application, not widely used, but widely used for display drivers are gold bumps. And this is where tab also comes into play sometimes. And gold bump is nice, soft material, easy to bond to for the tab tape. Sometimes these bumps are attached not through a metallic, normal metallic kind of bonding process, not like a welding process or a soldering process. In this case, you see there's some conductively coated polymer particles, and they just kind of get wedged between the trace on the flex film and the gold bump. And when the adhesive cures, it keeps those contacts in place. For narrower pitch and higher density, copper pillar bumps are preferred. And so the bumping process is pretty much like I showed before, but the majority of the bump is a copper, and then over the top of it is a tin or solder layer. So again, I think, well, I had the opportunity to work on this project. This is back in 2005 with a company called TriQuint, now part of Corvo. And we worked on copper pillar bumps back then, probably about 3 years before the industry really picked up on it. But what drove them to adopt copper pillar bumps was that they could get much better thermal performance than with wire bonds. And all the interconnect was contained within the footprint of the chip. So for them, they were able to shrink their part in comparison to competitors' parts. So the main reason to use a copper pillar bump is for finer pitch. So you can shrink the pitch down to 55 or 35 micron. You can have high bump density, tens of thousands of bumps on a chip. Good current carrying capability, good electromigration resistance, which is a particular type of failure that can occur. But the downside is, with respect to pitch, if you go below about 80 microns in pitch, you have to change the joining process, and you have to change it from like what we call a mass reflow process in an oven into a thermal compression bonding process where we're doing one chip at a time. There's all kinds of ways people design their bumps. The most typical in the industry is something like on the right, kind of a, I don't know how I describe that bump, but that would be more typical, that kind of format. But if you look at how Intel designs their copper pillar bumps, it's quite different. Very narrow at the bottom and kind of spreads out very wide at the top, kind of almost like a lily pad, I guess. And then we have something we call micro bumps. So there's no real definition of what makes a micro bump versus a standard bump, but essentially it's a very tight pitch, a small bump. So an example might be 10 micron wide bumps on a 30 micron pitch. And these are typically for chip-to-chip connections. So you're seeing, and typically if you're talking about chip-to-chip connections for stacked chips, they're going to have TSVs. So these would be the connections from one TSV to another TSV, as is shown here. There are other bumping processes. Some are electroless, so you don't need the seed layer. The material can be applied all within a chemistry bath, but these are not in high use. And again, depending on the application, people have looked at all kinds of strange bumps. So I'm just showing an example here where people were looking at making, they call them polymer bumps. So essentially creating a trace that went over a raised polymer portion and using that as a bump for interconnection. So the trend in packaging always is smaller and denser and lighter, thinner. And so if the package is getting smaller, that means the bumps have to be getting smaller too. And so that's what the trend has been over time. And starting with solder bumps and then going to copper bumps and smaller copper bumps. So, as I mentioned before, you know, if you're going to join, you have to have appropriate metallurgy on each side of the joint. So, if there is a tin cap or solder on the bump, there has to be an appropriate pad finish on the substrate that you can join to, or whatever the substrate might be. So for a solder reflow process, it's a pretty straightforward process. We typically use a material called flux to help initiate and sustain the bonding process, and the flux essentially removes oxides from the materials. You place the chip, you apply heat, and if it's not fine pitched, then that can be done just in an oven with many parts at the same time. Clean off the flux, underfill it, and cure the underfill. And that would be a typical solder reflow flip chip process. You don't have to just use flux. There are other ways to reduce oxides, so you can do a plasma processing to reduce the oxides prior to doing the joining. You have a limitation in time between when you do that kind of process and when you do the joining. Or you could solder in something called a forming gas or formic acid. I won't go into all the detail here, but there's a kind of a prescribed way to go through a soldering process, a preheat and a soak time, and then you want to reach your reflow temperature, but then cool as quickly as you can. And this is all kind of very well thought out, how to do these processes. And what results is a joint that's really a combination of the materials on each side of the bond. And you form what we call an IMC, or intermetallic compound. So, for example, if you have copper on one side and you have a tin-based solder on the other, you're going to form intermetallic compounds that are elements that combine both copper and tin. So you might have something like Cu6SN5 or Cu3SN. So these, and that's what the joint is. That is what holds things together. This is more detail on what these IMCs look like. And they're diffusion-based processes, so depending on where you look, which side of the joint you're closest to, you'll get different intermetallic compounds. So after we do the joining, then we clean it. There's just showing some of the possible issues that can arise in bumping. You see some voids there. Interestingly, voids generally are not a problem. You could have even as much as 30% void in a bump and in a solder connection, and it's almost never a problem. But the ones on the right are real problems. These are non-wets where the joint was never properly formed between the two sides. So I mentioned that if you go below about 80 micron pitch, we have to go into something we call thermocompression bonding. So this is no longer mass reflow in an oven where you can do many parts at the same time. This is each chip individually is bonded to its substrate. And you can see the process there in the diagrams where in this case, NCP or non-conductive paste is being put down, and then the chip is held by a bond head and pushed through that paste onto the bond pads, and the temperature is raised so that the solder reflows, and then the bond head is cooled down. As the solder solidifies, the bond head is removed. So the trade-off here is that now you have a fairly slow process, and you're doing one chip at a time, but you can do finer pitch. So you can see, again, there's all kinds of issues that can arise. The one on the left is a non-wet. The joint hasn't been made. In the middle, you kind of over-bonded, and you kind of get the solders squishing out at the sides. And then that one on the right is misaligned. So it's, if you're working on the line, these would be all things that you'd work to correct and make sure it never happen. Yeah, I guess it's just going back to the history. So this really came about in 2010. So Amcor developed this thermocompression bonding process for fine pitch back then, and it's been widely adopted since then for high density parts. So, the major benefit of fine pitch copper pillar bumps is just that they're at a fine pitch. So you can get many more I/O on your chip than you can with a solder bump process. Not as much used, but there are other ways to join. This one's called LAB, or laser assisted bonding. I'm not sure why it ever got the name laser assisted, because it's essentially just laser bonding. But essentially you're shining a laser either from the top or the bottom through the materials, one of the materials that you want to join, to be able to reflow the solder. Let's skip that. And this is called reverse LAB, so you're just coming from the backside. You're coming through the substrate, but essentially the same kind of process, using the laser to heat up the joint until it reflows. So TSVs, what I referred to before, they're through silicon vias. So they have a minimum pitch of about 20 microns, so we're getting down into this very small pitch realm for packaging. And they require micro bumps, not regular standard size bumps, to connect to those TSVs at that kind of pitch. So the micro bumps often are just miniature versions of a standard copper bump, and you can see one there, especially on the right. The copper part, and then in this one in particular has a nickel layer over it, and then a solder. And this is in close-up. So on the left, what you're seeing are stacks of DRAMs with TSVs. So this would be something that would be used in very common for high-performance application today, something called a high bandwidth memory, or HBM. Where numbers of DRAM are stacked together. So the obvious advantage of stacking, 3D stacking of chips, is that you get a very small footprint. And it can be relatively thin if you thin the chips before you stack them. Very high functional density and very short wiring. So the short wiring helps with the performance. Not only performance in terms of electrical performance and speed of communication, but also power. So if you can imagine, there's a driver on a chip that needs to send a signal. If it has to send a signal a long ways, that driver has to take more power. But if the driver is sending a signal a short distance, it requires less power. So one of the things that designers look at is the power per bit in sending a bit of memory from one place to another. So you can reduce, when you 3D stack, you can reduce the power as well as improving the performance. The other thing that you can do with 3D stacking is allow for what we call heterogeneous chips or heterogeneous interconnects. So it just essentially means that we're using different types of chips, which is not so easy. If you talk about, we talked before about system on chip, where there was a time when everybody was trying to integrate everything on one chip, but that becomes very difficult. So for example, a logic wafer fab process is quite different from a memory wafer fab process, and trying to make those all on one chip is very problematic. So never got picked up really, but what people had noticed in research papers is that if you made two surfaces very smooth and of the same metal, and you put them in contact with each other, and with heat, you can accelerate the diffusion, interdiffusion at the atomic level, and make a bond. As I said, it never really got adopted at the packaging level, but we'll see in a minute that it's going to be very important for the industry. This is kind of goes back to what I was showing before with that Samsung display part. So we can use other kinds of films, conductive films with conductive particles in them to join from one side to the other. So let me talk a little bit more about RDL. We talked a little bit about it before, but I'll kind of expand on it. So what I'll call the first generation RDL was really, and where it got its name for redistribution layer, was that its purpose was to redistribute pads from the outside of the chip, the outer bond pads, to an internal area array, so that the chip that might have been designed for wire bond, or just because the IOs were on the perimeter, was designed with the bond pads on the perimeter, could now be used for flip chip bonding. So it's not too much unlike another interconnect layer on the wafer. So these would all be done at the wafer level. And in fact, if you're looking at these devices, unless you really know what you're looking for, it can be difficult to tell what's a normal interconnect layer and what's an RDL layer. And these were also used on DRAM chips. If you recall at the very beginning, I said for DRAM chips, often the baud pads are down the center of the chip, and it's kind of the opposite problem as the last slide. So now the bond pads are in the center, and you want to bring them to the perimeter of the chip. So RDL was used in that case also. So the advantage of RDL is because it's a thin film technology, you can offer dense interconnects, small via sizes, small trace lines and spaces, and you can make them multi-levels. So the part on the right there is an Apple application processor, so the main chip in an Apple cell phone in a type of package that uses RDL there. You can see the thin film RDL on the bottom. We talked about this before, so I don't think I'll reiterate. This is just showing what some of the equipment looked like for some of these processes for either the underbump metallurgy for flip chip or for RDL. We start with seed layers, and that's usually a sputtered material, which means that you're just impinging on a surface of a metal with high energy particles, and you're actually knocking metal atoms off, and they deposit on the substrate that you want them to deposit on. And then often we use electroplating for forming either solder or copper bumps. And so there's just picture of what one of those pieces of electroplating equipment looks like. So kind of the second generation and third generations for RDL. So RDL purpose sort of changed over time. So the second generation was really for what we call wafer level packages. So this essentially is, we're not dicing a wafer before we're packaging, we're dicing the wafer after package. So we call it a wafer level package because all the packaging is done at the wafer level. And I think I'll show in a second another slide that better illustrates this, but it's kind of like a flip chip package, but with just bigger bumps on it so that it can be mounted directly to a printed circuit board. And for a wafer level package, by definition, everything fans in, we say, from the perimeter. So everything routes from the perimeter inside on top of the chip. But there became a need for people wanting to do the same kind of thing, but with more I/O that wouldn't all fit on the chip. So this fan-out process was created, and we call this a fan-out wafer-level package, the picture on the lower right there. So we're using the mold compound essentially to extend the surface of the chip, and then we can put the RDL on top of both the chip and the mold compound. And then the fourth generation really is to use it for electrical performance, to extend the interconnect on the chip itself. So what you're seeing on the right, you're seeing an Intel chip. And above the passivation layer are formed these RDLs. And that's kind of one of the ways we distinguish what an RDL is from a chip interconnect. If it's below the passivation layer, that's interconnect. If it's above the passivation layer, we call that an RDL. And you can see here in the green and blue, what they're using this for is power distribution on the chip. And so RDL, because it's thick and wide in comparison to chip interconnect, is a good choice for power distribution network. And if you can take that kind of a step further. So this is an example again of an Apple application processor. And they're using the bump layer also as an RDL layer for the power distribution network. And on any chip, there's different well, not on any chip, but on SoCs or logic chips, often there are different areas that run at different voltages. And so your power distribution network may be split into different voltage levels depending on the transistors and the function that's required. And so in this case, Apple is using that RDL layer to distribute different voltages to different parts of the chip. And then kind of the fifth generation of RDL is for 2.5D and 3D packaging. So you can use it to make a 2.5D interposer. It's a component of the TSVs and the 3D chip stacking. So it's become quite common in high performance packaging. So even though it started as really a wafer fab kind of oriented technology, it's found wide use in packaging now. So I mentioned that we can even use printed wiring board or printed circuit board micro vias as interconnects. So sometimes we have things we call embedded die. So this is kind of similar to the embedded bridge that I showed before, the bridge in the laminate substrate. But you can put the active die inside the substrate while you're laminating it, and then use the lasers to create vias in the dielectric and expose the bond pads and then create interconnects in those vias. So you can connect to the chip that's embedded within the substrate. this is just going through the process steps I just described, but you can see there on the lower left in the picture kind of what these might look like. There's a micro via that's connected to a pad on the chip. The pad has been coated with a kind of a thick copper layer because if you didn't do that, the laser could burn through a normal chip pad, so you have to modify the pad on the chip. So this is an example of a part made that way. So in the center of this part is an embedded die with the connections by microvias. So what you can see in this case is that opens up the top of the package substrate where they can mount other components. So in this case, they're mounting inductors and capacitors on the surface. So you can imagine there's certain advantage to this. You can have short interconnects and thin packages because your chip is inside the substrate itself. Small area, open up the packages as the last slide showed for other devices to be mounted. But it hasn't really taken off in the packaging world. It's not widely used, and I think part of the reason is that typically you would have to go to your laminate substrate supplier to initiate this process, and most laminate substrate suppliers really don't understand packaging technology or dealing with wafers and chips, so not widely used. So talk a little bit about through silicon vias. So as I said before, these are vias that extend all the way through the silicon chip. And so you can route signals from the top to the bottom or front to back of the chip. And they're formed by this specialized plasma process we call dry. And the process is pretty interesting in that you have alternation of an etching step and then a deposition of a polymer on the sidewall, and then you etch again, and you continue this down through, and so you get this kind of scalloped edge of the via if you look closely at that picture in the center at the bottom. But these vias can have very high aspect ratios. By aspect ratio, I mean, how deep is it compared to the diameter? And so that's very advantageous because you can have very dense pitch then. So this is how TSVs are formed in the fab. You can imagine you could form the TSV at the very start. You could form the TSV in the middle of your fab process, or you can form the TSV at the end of the fab process. But in most cases, it's formed in the middle, so we call this a via middle kind of process. So this part of the process would be done in the fab. So you have your FEOL, stands for front end of line. So that's the transistor formation parts, the ion implant, etc. And then you would do your TSV etch and fill the TSV with a conductor so that it's a conductive via. And then the interconnect layers would be built up on the end. The terminology there, BEOL, means back end of line. So just kind of the end processes of the wafer fab. And so then once that wafer with a TSV comes out of the fab, you thin it. And by thinning it, you expose the TSV and put a protective layer on it and grind again and etch and apply some material and essentially end up with now a TSV that can be used to interconnect to another chip. And the whole purpose of TSVs is really for 3D stacking. And so, again, when you want to densify, this is where it's used. Okay. So this is, again, just showing an example where a TSV might be used. So this is a CMOS image sensor. So I don't know if you're aware, but the cameras in your phone are actually semiconductor chips, specialized semiconductor chips that accept the photons and the light and convert those electrical signals and process them to create an image. And so what we're seeing here is we call it a tear down, but deconstruction of this package. And in this case, this is what we call a via last TSV. So the image sensor itself is mounted on what's called an ISP there. So it's an image sensor processor. It does the processing of the photons. And the CIS is a CMOS image sensor. So it's essentially the part that converts photons to electrons. And those two are bonded together. But the signals from the CIS have to be interconnected to the ISP. And so in this case, a via last TSV is used. So a via is formed after the chip has been formed and is used to interconnect. And you can see that on the very right, that kind of V-shaped structure is the TSV has been etched through the image sensor chip, and so that you can make a connection down to the image sensor processor underneath. So this is a better close-up of those interconnects. So I'm going to talk about something called hybrid bonding. You might see it also referred to as DBI or direct bond interconnect. But this is kind of where the industry is going to be going for very high performance. So I mentioned before that you can do copper-to-copper bonding, diffusion bonding at an atomic level, but it was never really adopted by packaging. It wasn't adopted in kind of the older times, but it's being adopted today. And it's going to be probably one of the most significant things in the packaging arena, in my estimation. So this is good for wafer-to-wafer bonding or wafer or chip-to-wafer bonding, or sometimes called die-to-wafer bonding. And essentially what you're seeing at the bottom are two different wafers. And this works only with copper interconnect processes. So you have to have a copper layer at the outside, and you planarize this copper layer, and you activate it with a plasma, and you bring the two wafers together. And the copper is formed within an oxide, silicon dioxide dielectric layer. And those dioxide layers will bond and hold the parts together, hold the two wafers together, and then you apply heat, and the heat expands the copper, and when they touch, they start to interdiffuse. So it's a very low temperature process, but the good thing about it is that it essentially can be done at the scale and the density of whatever the interconnect layer is you have on the wafers. So extremely tight pitch. This is kind of showing how this progresses. So you have to have very, very smooth wafers. You have to have the wafers processed such that the level of the copper is just below the surface of the oxide. So specialized process steps. But once you have that set up, the bonding process itself is pretty straightforward. And you can see here, this is showing that it's kind of a self-regulating process. As soon as you make that first connection in the interior of the wafer, that bond interface of the oxide will kind of continue by itself and spread so that the whole wafer is bonded together. So Sony was the first to use this. They used it similar to the part we just saw a minute ago to bond an image sensor chip to the signal processor. But it's used elsewhere today. But it is just on, I would say, the start of its use. This will become a widespread technology in the near future. So TSMC, if you're not familiar with them, Taiwan Semiconductor Manufacturing Corporation, they're the largest independent wafer fab in the world, but they also do packaging. And they're strongly supporting hybrid bonding. So, you know, if the industry leader goes a certain way, then others will follow. But they've demonstrated 12 high stacks of using this hybrid bonding technology. So we talked before about the memory wall and wanting to get the memory as close to the processor as possible. So AMD used this technology to do just that. They actually stacked their static RAM cache chips directly on the processor by bonding the interconnect of one of those chips to the interconnect of the other using hybrid bonding. And I guess, whoops. I want to point out one thing here too. So you can see here, maybe in the notes, so the bond pads are at 9 micron pitch. So I said before for micro bumps that we use to package TSV parts are maybe on a 20 or 30 micron pitch. So the advantage here is that the pitch can be quite tighter. The other interesting thing is that the hybrid bonding process is initially bond is done at room temperature. Anytime you can do something at room temperature rather than high temperature, when you raise the temperature, things start to expand differentially. Alignment becomes difficult. So if you can do something at room temperature, it makes the process that much easier. So once it's initially bonded, then you go into a lower temperature anneal process to join the copper. So it's a very forgiving process. The difficulty really just is in the wafer preparation. So kind of in summary here, really what we're talking about is pitch and density. And so I mentioned before that in packaging and wafer fab, it's always about trying to get denser and more stuff crammed into smaller space. And that's the situation here too with interconnects. So if you go from left to right, we're trying to see this progression of pitch and density. So as far as we know today, hybrid bonding is the best that we'll be able to do. And it's been demonstrated all the way down to a 2 micron pitch. So it's really at the semiconductor kind of level. This is saying the same thing, but I guess I can't emphasize again in terms of packaging and semiconductors, hybrid bonding is just starting, but it's going to be a very, very significant technology. So again, graphically showing what I just described in the other images, but you see the die bump pitch there in that kind of top orange color being much wider. And even though it's reducing, it's not going to get to the point of the wafer-to-wafer hybrid bonding or the die-to-wafer hybrid bonding. Surface mount technology. So we talked a little bit before about printed circuit boards, and that laminate substrates are essentially an extension of printed circuit board technology. And when you think of printed circuit boards, typically you're thinking of an assembly at a board level where all the components, all the packaged components are soldered to that board. So if you opened up, a desktop computer at home and you saw the little black components on a green board, that's what you're looking at. Those parts have been surface mounted to the board. But we also use that technology within packages. And so it's an important adjunct to our packaging technology. And especially for system in packages. Oftentimes we want to mount a lot of different things in a substrate. It's very difficult to see the small pictures, but that's pictures of our first SIP assembly line at Amcor when I was there. And if you looked at those pictures, a lot of that equipment would be the same as what you would find on printed circuit board assembly line, like we were talking about that Jabil has here in the country. So to make these kinds of parts, we're using the SMT technology. We usually do the SMT process first. So we screen a solder paste, we surface mount and reflow whatever surface mount components we have on the part. And then we would do the die attach, in this case wire bond, but it could be flip chip interconnect of the chips. And then we would mold over all of that and cut up the parts into individual parts. So encapsulation is a critical building block. It's really the way that we enclose and protect the chip. So it has mechanical protection, chemical, environmental protection. Can also include electromagnetic shielding. I'll show you some examples. So the encapsulation can be prefabricated as a kind of a housing. So you see some examples at the top. Not very widely used because those packages tend to be more expensive. So if the application requires it, of course we'll use it, but not generally used. In terms of organic or polymer types of packaging encapsulation, the simplest would be something we call a glob top, where you literally just dispense a glob of material over the chip that's already been mounted and wire bonded, in this case, to a little printed circuit board. It's the underfill for flip chip as a type of encapsulant, but probably the most common in packaging is molding. So you're seeing there on the right parts that are molded, including part of the apparatus of how the material is transferred from an initial container and down these runners and sprues down to the parts. Again, back a little bit to the history. So, the initial packaging was quite different from what we're doing today. So initial packaging was all about packaging single transistors. And so you see kind of interesting and what looked to be quite different packages on the left than what we normally see today. And then because the wafer fab processes weren't that great, and passivation wasn't that great, we relied also on the packaging to help protect the chips. So initial packages were what we call hermetic. So they were gas tight. Water vapor and gas could not penetrate the package. And then later on, we got feeling comfortable that we could design packages that were plastic encapsulated. So if you have cavity packages, then there's a number of different sealing operations that can be done. I won't go into detail here, but glass seals and metal seals and solder seals, etc. If you remember just from a couple slides ago, I showed some of the very earliest packages. Nothing ever seems to go away in packaging, so we still have the same kind of shape packages. We call them transistor outline packages, but they can be quite complex today versus the original packages that just held one transistor. So molding is this process where we take a material and we liquefy it and we somehow make it flow around the parts that we want to encapsulate, and then we cure it. And that is a very essential packaging process. So we can do this either with what we call individual cavities in a mold. A mold is just the outer shell that makes the encapsulant conform to the shape that we want. Or we can do that by molding over many sections of packages and then later what we call singulate or separate those packages into individual packages. And it's more efficient to do this kind of what we call mold array process, where we mold over many packages and then later singulate them. So this is just talking a little bit about this material, the electronic mold compound, or EMC. And it's that blow up again, shows you what I was describing. It's generally an epoxy resin, but highly filled with like silica particles to be able to control the mechanical properties of the material. There are specialty mold compounds, so you can imagine for certain optoelectronic devices, you might want the material to be clear. But in most cases, most cases it's going to be a black-looking material. This is a particular kind of molding process. We call it transfer molding. And we can have film-assisted transfer molding also, compression molding. If we want underfill on a flip chip, but we don't want to have a separate material, sometimes we just mold the underfill. So we can do that also. And you see on the very right, kind of in the middle, is what compression molding looks like. You literally dispense some of the mold material in the center of the wafer, and then you compress it between two dies, and the material spreads and covers the whole wafer. So double-side molding, if we want to have a package that has components on both the top and the bottom side, we might want to go through a process for double-side molding, and so that has become more popular recently, and especially for RF kind of devices. And excuse me, I need to blow my nose, so I apologize. Sorry about that. And then this is just showing some of the board connections you might have with double-side molding. I think later on I'll show you a real-life example of this, and we can look at it in more detail. So you can see here, this is a system in package. RF. RF stands for radio frequency, so typically like part of the communication change for a wireless device would be composed of RF components. And so oftentimes you want to have these components close together. And oftentimes the designers want to make sure these components, which are radio frequency and analog devices, function correctly without their customers having to do a lot of design. So the more they can design into a package, and so that has a known function, will lead you kind of into this system in package kind of concept of trying to put everything into the package and make sort of a subsystem that is known to work. But you can kind of see the complexity of how these start to become. You have multiple devices, as shown here in this diagram, but this is kind of true to real life too. Some chips are flip chip, some are wire bonded. You have surface mount components. On the outside, the F that we haven't talked about yet is a shield material. So you want to shield the whole inside of the part from electromagnetic interference. So this is an example of a real part. This is that acronym stands for an inductor in a power amplifier module that also includes a duplexer. So it's, again, kind of signifies there's many of these RF components all within the same package. So this part is a double-sided part, double-side molded, chips mounted on both sides. It also has filters in it and passive components and the EMI shield. And in this case, the connection to the EMI shield is created by a wire bond. So again, back to this concept I talked about before, if you're a packaging engineer, you learn all these building blocks and then you try and use them as you can. So in this case, the engineer is saying, oh, how do I make a connection to the outside of the package? I'll use a wire bond, which normally would be used for a chip interconnect. So again, in this realm of encapsulation, talking about here kind of how underfill started. So we call it capillary underfill. Capillary because there's a capillary force in a small space, and that tends to draw the material under the chip. But we can also use the molding material itself as the underfill and kind of get rid of one of those process steps. There's different types of underfill. Some we call no-flow underfill, so it's put down on the substrate before the chip is attached, so you don't have to flow it under the chip. So shielding, we just saw an example a second ago, but shielding is required to prevent electromagnetic interference, and it's critical for RF components. And it used to be always applied at the board level and has maybe over the last 20 years pretty much migrated to the package level. And not only on the exterior of the package, but sometimes on the interior of the package also. We want to shield one functional area from another functional area. And so we'll provide what we call compartmental mold, shielding within the mold compound. In terms of application methods, we can sputter. So I described that process before. Use a wafer fab or for RDL, but we can use it here for shielding also. Or organic material that has conductive fillers can be sprayed, or we can use wire bonds. And so this is just a cross-section of a sputtered thin film shield on the outside of a part. And so if you open your phone and you saw a part that looks kind of silvery, that's the shield that's been applied to the outside of the package. And wire bonds can be used also. So to form a good electromagnetic shield, it really depends on the wavelength of what you're trying to shield. There doesn't have to be a continuous metal film. It can have gaps in it as long as the gaps are small enough, respective to the wavelength that you're trying to shield. So in that case, these wire bonds, even though they have wide gaps between them, are an effective EMI shield. So this is just a close-up of that part we looked at before, of where the wire bond is being used as a compartmental shield, but also connects to the outside, and showing that connection between the wire bond and the thin film that's been applied. The other thing that's made its way into the packages themselves are antennas. So all wireless devices are going to need antennas. So if we look at this part as an example, this is a 5G antenna. So if you have a 5G phone, you have an antenna. You probably have 2 or maybe even 3 antennas that look like this inside your phone. And so this is actually, it's in a package. And it's got a transceiver, and it's got a power management IC on a substrate, but the substrate also has antennas built into the laminate layers. So this functions as what we call antenna in package, or AIP. And this is the same, just a cross section of the same part. So the antennas would be on the bottom side of the substrate, on the opposite side of the core, and obviously the chips are on top. Okay, so we talked a lot about the building blocks, and we went through interconnect technology, encapsulation technology, things like that. So now I'm just going to talk for a little while about the package types that you might see, because there's a lot of different types. Not to try and have you understand every single one of these package types, but just to give you an introduction of the different types that are out there. So because of history, packages started out as what we call through-hole devices. There were, in the printed circuit board where the packages were going to be mounted, had holes in them, and the packages had pins typically, and those pins would extend through the holes, and then the solder could be applied to the bottom of the board. You can maybe imagine, just by looking at this diagram, that it's kind of inefficient. You're only using one side of the board for this type of assembly. These are early examples of through-hole parts. So you can see this kind of transistor outline package I was talking about before on the left, and early dual inline packages on the right. So these were the kind of the workhorses in the early days. But then people started to realize that, hey, if we could mount these packages and components on the board without having to have holes through the board, we could radically increase the density, and we could mount things both on the front and the back. And that was really the evolution to surface mount technology. And it goes back, all the way to the 60s, maybe late 50s even. People were thinking about this. And some of these packages, once they get designed, they stay around forever. So this is an example of a progression also of size that is pervasive to packaging. So you're seeing on the left a certain, we call it SOT package, or small outline transistor package, and how it's shrunk over time. I guess the other thing to think about here is, to me, when I first got into packaging, it was mind-boggling, the types of volumes of units that we dealt with. So in this example, I'm saying that Philips had developed one of these packages. They shipped 30 billion of these in 2018. I mean, it's just an astounding number. When I was at Amcor, when we would talk about one of our product lines and its unit volume, we would talk in millions of units per week. Because if we talked in anything less that kind of quantity, the numbers got too big, and we confuse ourselves. So many of the earlier speakers at the start of the day were talking about the pervasiveness of semiconductors. I guess this is another way to think about it. When you want to, support the cell phone industry, or you want to support the auto industry, et cetera, the numbers of units that you need to do that is just astronomical. So we saw a little of this before, but this is a typical lead frame package. You have a lead frame as the substrate, the die attached material that we talked about that attaches a chip to the substrate, a wire bond as an interconnect, and the encapsulation is the mold compound. So very classic, not like really new or advanced technology, but very widespread technology. And so you go from very small, like essentially 1 by 1 millimeter, to very large, 40 by 40 millimeter parts, and fairly thick down to fairly thin parts, as shown in that diagram at the lower right. So there are a lot of variations of this type of package. And then there's variations on the leads too. We can have leads extend from the edge, from 4 sides, from 2 sides. The numbers of leads can go from 2 to the 300 range maybe. And in some cases we have no leads at all, and that goes back to the QFN package I introduced before, which has become very popular. And the lead shapes themselves can be different. They can kind of come out in sort of an S shape, or they can come straight out, or be wrapped under the part. And when you have leads that extend from the package, you have to go through this process we call trim and form. So as you recall, that lead frame is all a planar piece of patterned, typically copper material. And to get the leads in the shape, they go through a series of punch and dies that form those leads into the final form that you want. And that's what the progression is showing at the bottom. These types of lead frame packages, most of them are plastic molded, but they can be ceramic that are sealed in some fashion. And if they're ceramic, they would typically have a cavity. And then there's various variations of these types of packages that help with the thermal performance of the part. So depending on how much power the chip dissipates as heat, then you may or may not need some kind of thermal enhancement. And so these are showing some different ways that thermal enhancement can be added to a lead frame package. And this is just showing some of the variety. So this is just a sampling too. This isn't all of them. And there are many, many standardized packages out there originally developed for a very specific application and got adopted by other applications. And still more. There are non-lead frame packages, also wire bonded packages. Kind of that one in the middle with the pins on it, a pin grid array package. That used to be the preferred package for microprocessors maybe 30 years ago, before the switch was made to flip chip and laminate substrate processing, processor packaging. And then a very popular introduction of a new packaging type back in the 90s was something we call a plastic ball grid array. So instead of having pins on the bottom of the package, we have balls So this is obviously a surface mountable package. And so again, you can increase the utilization of the printed circuit board and have these types of packages on both the top and the bottom. And there's many different types, sizes, and numbers of balls on these different PBGAs. And a subset of PBGAs is called fine pitch, so essentially the same kind of structure, but just smaller pitch and smaller mounted height. So I'll spend the next little bit talking about advanced packages. So there's no like specific definition of what an advanced package is. Sometimes we just look at what's more recent to say that it's advanced, and so that's one way to look at this. But generally, we're trying to employ a little bit more sophisticated techniques than maybe other packages do. And so I'll go through this list one by one. So I introduced this before. This is the quad flat no lead package. It's a type of wire bond lead frame molded package. So in that sense, it's kind of traditional, but what makes this different really is that there's no leads extending from the package. And the leads are, bond pads are all on the bottom, which also means that the chip bond pad can be on the bottom, or package bond pad can be on the bottom where the chip is, so it offers a good thermal path. And you can imagine that rather than leads that extend out beyond the package and solder to the printed circuit board, the connection here from the chip to the printed circuit board is quite short. It's just that wire bond connection to the lead frame, which immediately goes down to the printed circuit board, which isn't shown here. So it's quite good performing package and made with traditional processes and materials, so it's not a very expensive package. We can also use flip chip within that kind of package. In fact, in any kind of lead frame package, we can use flip chip rather than just wire bond. So essentially there, we're just making sure that the appropriate lead finishes on that portion of the lead frame where we want the flip chip to attach to. And in general, anytime we move from wire bond to flip chip, we're improving electrical performance. We're reducing the electrical length that the signal has to go, reduce the inductance. I'll skip that. So lead frame packages have become a lot more interesting over time, I guess. It used to be that everybody would stick within just a standard kind of package and a standard way of applying a chip, one chip per package. But over time, these have become multi-chip, or in this case, they're attaching big inductor on the top of the lead frame, et cetera. So it's really up to the imagination of the designers and the packaging engineers what can be done with any of these packaging technologies. And this is the same part. It's just showing the electrical advantages by integrating things inside the package. And more examples, again, all on lead frame. We can enhance the QFN further. So, for example, this type of package can support multiple chips, but we can also put clips in the package to replace the wire bond. So I mentioned this kind of technology before, but this is a way to improve current carrying capability as well as thermal power dissipation. So you can see there the market share over time. So in terms of unit volume, the QFN is widely used, probably more than any other package type. And we talked about this a little bit in terms of the interconnect, but these are varieties of flip chip packages shown here. So again, anytime we have bumps on the chip as the interconnect, that would go into a flip chip package. And again, one of the major drivers for going into flip chip versus wire bond is the performance. Electrical performance is much better, but also we can support much higher density of I/O. So if you have a high I/O chip, chances are it's going to be a flip chip. So this is the wafer level package I described a little bit before, but this kind of maybe better explains it diagrammatically of what the difference is between a traditional packaging flow and a wafer level packaging flow. So on the top, in a traditional flow, we take the complete wafer from a semiconductor fab and we dice it into individual chips, and then we package those individual chips. But for wafer level packaging, we're doing the packaging at the wafer level. So we have the initial wafer and the packaging applied onto the wafer, and then after the packaging is applied, we dice it into individual packages. And again, that implies that these are going to be chips that are relatively limited in I/O because all the I/O is within the outline of the chip. And we put solder balls on these wafer level packages that are large enough and a wide enough pitch that they can be directly surface mounted to a printed circuit board. And these came about in the late 90s. A company called National Semiconductor is a picture of the first parts that came out. But you can see it looks essentially like a flip chip. And essentially is like a flip chip, except that the bumps on it are solder balls. And unlike flip chip, where we typically electroplate the bump material, on wafer level package we usually use a preformed solder balls, and we drop them onto the surface of the chip into some flux that has been placed on the bond pads, and then just reflow them in place. So the key here is, again, having those bumps, solder bumps on the wafer level package be big enough and wide enough pitch so that they can go through a standard surface mount process. So wafer level package is really not much of a package to it, a few thin film layers and a solder ball. So that has, but because of that, it's a very thin package, right? It's not much thicker than the chip itself. It doesn't extend beyond the edges of the chip, so it's no bigger than the chip. So in any areas where space and thickness need to be optimized, this is the very good package. And so it has been widely used for applications like mobile phones. And as an example, there's probably about 20 wafer level packages in iPhone 15. I think I'll skip, this is kind of detail about how you might form the bump on these. So again, kinds of applications here, typically applications that are mobile. And so this is just an example. This is a Samsung transceiver from their S8 mobile phone. But the solder balls on these look deformed because as you remove these from the circuit board, a lot of the solder stays on the circuit board. So you're seeing remnants of what were solder balls. Yeah. Sure.
Aquí estoy. Miren, vamos a tomar una pausa, es momento del almuerzo. Hemos tenido una mañana.
Pero antes vamos a darle un aplauso y un masaje. Ahora sí, entonces, explique el proceso de que vamos a ir.
Ok. Entonces, vamos a ir al almuerzo por orden de este lado.